Let's dive in. All right, makers, builders, and curious minds. Adam here, and today we're diving headfirst into the guts of modern electronics to uncover a component that is absolutely everywhere, yet so few people really understand it. I'm talking about the capacitor. I know, the name sounds a little intimidating, like something out of a super complex physics textbook. But I promise you, by the end of this, you'll not only get what it is, but you'll also appreciate the sheer genius behind this tiny, powerful workhorse. We're going to peel back the layers, get our hands metaphorically dirty, and reveal the magic that makes your gadgets tick. So grab your safety glasses. Not that you'll need them for reading, but it sets the mood. And let's get started on this awesome journey. Think of a capacitor as a tiny, ultra-fast battery. Seriously, that's the core of it. While a regular battery like the one in your TV remote stores a bunch of energy and releases it slowly and steadily, a capacitor does something a little different and a lot cooler. It charges up with electrical energy in a flash, we're talking fractions of a second, and then it can release all that stored energy in one massive, instantaneous burst. It's like the difference between a water hose and a water balloon. The hose gives you a steady stream, but the water balloon gives you a big splash all at once. This ability to charge and discharge with lightning speed is what makes capacitors so incredibly useful in the world of electronics. Let's get even simpler. Imagine you're trying to fill a bucket with a leaky hose. The flow is weak and inconsistent. Now what if you first filled a separate, smaller bucket from a tap and then, whoosh, dumped that full bucket into your main one? That's what a capacitor does. It smooths out the flow of electricity. It takes in the lumpy, inconsistent electrical current, stores it up for a microsecond, and then releases a nice, clean, stable stream of power. This smoothing action is crucial for sensitive electronic components that can't handle jerky or unstable power. It's the silent guardian protecting the delicate circuits inside your favorite devices from electrical hiccups. So, why should you care about this little electronic doodad? Because understanding the building blocks is the first step to becoming a true maker. When you know what a capacitor is and what it does, you're one step closer to diagnosing a problem with your stereo, building your own crazy gadget, or just having a deeper appreciation for the technology that surrounds us every single day. We're not just going to talk about theory. We're going to break down how they're made, where they hide in plain sight, and why they are the unsung heroes of the circuit board. Stick with me, because this is where the real fun begins. Let's demystify this thing together. So, what kind of sorcery is packed inside these tiny cylinders and discs? It's surprisingly simple and totally brilliant. At its heart, a capacitor is basically an electric sandwich. That's it. You have two layers of a conductive material, which we call plates. Think of these as the two slices of bread in our sandwich. These plates can be made of all sorts of conductive stuff like aluminum foil or other metals. The key is that these two plates are incredibly close to each other, but, and this is the most important part, they never ever touch. If they touched, it would just be a wire, and the magic would be gone. The separation is everything. What keeps these two conductive plates apart? That's the filling of our electric sandwich. This middle layer is called a dielectric. Now there's another fancy word, but don't sweat it. A dielectric is just an insulator, meaning it's a material that doesn't conduct electricity well. This could be anything from plastic, ceramic, or even paper to a special chemical paste. The job of the dielectric is simple but critical. It acts as a barrier, preventing the electrical charge from jumping directly from one plate to the other. Instead, the charge builds up on the plates, creating an electric field right in the middle of that dielectric material. It's like a standoff between two armies, with a no man's land in between. Let's visualize how this electric sandwich works. When you connect a capacitor to a power source, like a battery, positive charges from the battery's positive terminal start to pile up on one of the conductive plates. As these positive charges accumulate, they push away the positive charges on the other plate, which then flow back to the battery's negative terminal. This leaves one plate with a net positive charge and the other with a net negative charge. An electric field forms in the dielectric between them, and that field is where the energy is actually stored. It's like stretching a rubber band. The energy is held in the tension. The beauty of this design is in its simplicity and versatility. The amount of energy a capacitor can store, its capacitance, depends on three things. First, the size of the plates. Bigger plates mean more room for charge to hang out. Second, the distance between the plates. The closer they are without touching, the stronger the electric field and the more energy it can hold. And third, the type of dielectric material used. Some materials are way better at holding an electric field than others. By tweaking these three ingredients, engineers can design capacitors for thousands of different jobs, from tiny ones in your watch to massive ones in a power grid. Now that we know how these electric sandwiches are built, where do we actually find them in the wild? The answer is literally everywhere. Let's start with something you probably use every day, a camera flash. Have you ever wondered how that incredibly bright flash of light is created from a couple of small batteries? That's a capacitor showing off its superpower. The camera's batteries are too weak to create that intense flash on their own. So they spend a few seconds slowly charging up a capacitor. Once it's full, you press the shutter button and bam! The capacitor dumps all its stored energy in an instant, firing the xenon flash tube. It's the ultimate power burst specialist. Another huge job for capacitors is in audio equipment, like your stereo amplifier or your electric guitar amp. When you're listening to music, the sound waves are represented by a fluctuating electrical signal. This signal has both alternating current and direct current components. The direct current part is just background electrical hum that you don't want to hear. Capacitors are perfect for this job because they block direct current while letting the alternating current signal, the actual music, pass through. They act as filters, cleaning up the audio signal so all you hear is crisp, clear sound without that annoying buzz. They are the silent gatekeepers that make your favorite songs sound so good. Think about your computer's motherboard or the power supply for your game console. These devices need incredibly stable, clean power to function correctly. The electricity coming out of your wall outlet can be a bit messy, with tiny spikes and dips in voltage. Capacitors, especially the big cylindrical ones you see lined up on circuit boards, act as tiny reservoirs of power. When the voltage from the wall dips for a millisecond, the capacitors instantly release their stored energy to fill the gap. When there's a voltage spike, they absorb the excess energy. They are the shock absorbers of the electronics world, ensuring a smooth ride for all the sensitive microchips. Finally, let's talk about timing. Capacitors are essential components in timing circuits. By pairing a capacitor with another component called a resistor, you can create a circuit that takes a specific amount of time to charge and discharge. This is the basis for all sorts of things, from the blinking light on your Wi-Fi router to the timer that controls your microwave. The rate at which the capacitor fills and empties acts like a pendulum in a clock, creating a reliable beat that other parts of the circuit can follow. From a camera flash to a blinking LED, these little powerhouses are the unsung heroes doing the heavy lifting behind the scenes. All right, let's get into the workshop and see how these things are actually made on an industrial scale. It's a fascinating process of precision engineering. The most common type of capacitor, the kind you see everywhere, is the electrolytic capacitor, that little can-shaped component. It all starts with the plates. Instead of flat plates, manufacturers use two incredibly long, thin sheets of high-purity aluminum foil. One of these sheets, the anode, is chemically treated, or etched, to make its surface incredibly rough and porous. This vastly increases its surface area, allowing it to hold way more charge, just like a crumpled piece of paper has more surface area than a flat one. Next up is our dielectric, the filling for our sandwich. For an electrolytic capacitor, this isn't a solid sheet of plastic. Instead, a thin layer of aluminum oxide is grown directly onto the surface of that etched aluminum foil through a process called anodizing. This oxide layer is an amazing insulator, but it's unbelievably thin. We're talking nanometers thick. This is key because, as we learned, the closer the plates, the higher the capacitance. To make contact with the oxide layer, a sheet of paper is saturated with a conductive liquid or gel called an electrolyte. This electrolyte-soaked paper is placed on top of the oxide layer and acts as the second plate, the cathode. So now we have our layered sandwich, the etched aluminum foil, anode, the ultra-thin oxide layer, dielectric, the electrolyte-soaked paper, cathode, and another layer of plain aluminum foil to make a good electrical connection to the electrolyte. That's a lot of layers. To make it all fit into a tiny package, this long strip of layered materials is tightly rolled up, just like a jelly roll or a sleeping bag. This clever rolling process allows for a massive amount of surface area to be packed into a very small cylindrical volume. It's a brilliant piece of mechanical engineering that allows for high capacitance in a compact form factor. Finally, this rolled-up bundle is inserted into a small aluminum can. The two foils have leads attached to them, which stick out the bottom to be soldered onto a circuit board. The can is then sealed with a rubber bung to keep the electrolyte from drying out. And there you have it. A finished electrolytic capacitor, ready to store and release energy in your favorite piece of electronics. From simple sheets of foil and paper to a high-precision electronic component, it's a beautiful example of manufacturing at its finest. Every step is carefully controlled to create a reliable and powerful little device. It's easy to overlook a component as small and common as a capacitor, but let's be clear. The modern world would not exist without them. I'm not exaggerating. Every single device with a microchip, from your smartphone to your car's engine control unit, from the servers that run the internet to the medical equipment that saves lives, relies on capacitors to function. They are the bedrock of digital electronics. Without their ability to filter power, store energy for quick bursts, and create timing signals, our circuits would be unstable, noisy, and completely unreliable. They are the ultimate support system for the more famous components like processors and memory chips. Think about the incredible push toward renewable energy and electric vehicles. What do you think is one of the key components inside the complex inverters that convert DC power from solar panels or batteries into the AC power that runs our homes and charges our cars? You guessed it. Massive banks of capacitors. They are essential for smoothing out the flow of energy, handling huge surges of power, and ensuring the electricity produced is stable and clean. As we move away from fossil fuels, the demand for bigger, better, and more efficient capacitors is only going to grow. They are at the very heart of the green energy revolution. Furthermore, the development of new capacitor technology is pushing the boundaries of what's possible. Scientists and engineers are constantly experimenting with new materials, like graphene and advanced polymers, to create supercapacitors. These are capacitors on steroids. They can store almost as much energy as a battery, but can charge and discharge millions of times without degrading and in a matter of seconds. Imagine a phone that charges fully in 30 seconds, or an electric bus that recharges at every stop in the time it takes for passengers to get on and off. That's the future that supercapacitor research is building, and it's incredibly exciting. So the next time you see a circuit board littered with these little components, take a moment to appreciate them. They may not have the glamour of a CPU, but they are doing some of the most critical work. They are the quiet, reliable soldiers of the electronic world, providing stability, power, and timing to every gadget we love. Understanding the humble capacitor is understanding the fundamental language of modern technology. They are a testament to the power of simple, elegant design, and a reminder that sometimes the most important parts are the ones you barely notice. They are, without a doubt, a cornerstone of our technological civilization. Wow, what a journey! We've cracked open the humble capacitor, demystified its electric sandwich design, and seen how it powers everything from your camera flash to the future of green energy. My goal is always to make science and engineering accessible to everyone, to show you that the complex world of technology is built on ideas that you can totally understand. I hope you're walking away from this feeling a little more knowledgeable and a lot more curious about the amazing gadgets that fill our lives. This stuff isn't magic, it's just brilliant making, and you are absolutely capable of getting it. But now, I need a little bit of energy from you. Creating content like this, diving deep into topics, breaking them down, and sharing that knowledge takes a huge amount of effort. And your support is what keeps this whole operation running. If you found this interesting, if you learned something new, or if you just enjoyed the ride, do me a huge favor and hit that like button. It's a simple click, but it tells me that I'm on the right track and that you're finding this content valuable. It's the fuel that keeps my creative engine turning, and it genuinely means the world to me. And if you really want to help power up this channel, share this essay with someone you think would find it cool. Maybe it's a friend who's into electronics, a student who's just starting their science journey, or just someone who loves to learn how things work. Spreading the word helps us build an amazing community of curious minds, and it allows me to reach more people with this message of discovery. And of course, if you haven't already, please hit that subscribe button. Subscribing is the best way to make sure you don't miss out on our next adventure. We have so many more myths to bust and technologies to unveil. Thank you truly for spending your time with me today. It's an honor to share my passion with you. Your likes, shares, and subscriptions are more than just numbers on a screen. They are a direct line of support that enables me to keep building, keep exploring, and keep creating more quality content for you. You are the reason I do this. So thank you for being a part of this community. Now go out there, stay curious, and maybe don't try to take apart a capacitor yourself. Leave that to the pros. Until next time, keep on building.